Sir. Hello, friends. Welcome. Today we will look at the breaking of synchronous motor. Uh, in the case of synchronous motor, the omega t characteristics, if you see, this is the omega, the speed, this is the torque. Omega is positive running clockwise, torque is positive helping to operate as motor driving it. So this is the motoring mode. So this is quadrant 1. In quadrant 1, the motor being synchronous speed obviously runs at omega ms, and this represents the motoring mode of operation. Now in quadrant 2 it is regenerative type. The torque, you see, negative, the power is fed back, and the speed is omega ms only. It is synchronous motor, and the power is fed back. It's regenerative action. But the braking doesn't happen in a normal way. That is the problem with synchronous motor, because that speed remaining constant as long as it is a synchronous motor, na? So when the regenerative action happens, it happens with speed remaining constant only. So the normal braking doesn't happen. And to overcome this and realize the braking of the synchronous motor, we go for the dynamic braking. We have already come across different types of brakings. The dynamic braking is one of them, and in that dynamic braking, what we'll do? So it is clear from the figure, the synchronous motor braking, what we call this regenerative braking, the feedback of power, the speed remains constant, and to have the real braking, dynamic braking is employed. So during dynamic braking, what actually is done? Look at this. Synchronous motor, stator is the, its rotor is the stator with 3 windings, rotor with the poles. Here the electromagnetic poles are shown. Now during braking, the supply to the stator is cut off. The stator windings are shorted. Can you see? The stator windings are shorted. And the rotor, the current IF is controlled. So we have the stator, we have the rotor, stator windings shorted with additional external rheostats if required. Okay. So now the procedure for braking will be this. Input to stator is cut off. Otherwise we used to supply 3-phase AC, na? That input is cut off. And stator windings are shorted to form closed loop, and field current is still maintained. Now when that is done, look here, due to the earlier running operation of the motor, this rotary is rotating. Now we are having the field current here intact. That means the magnetic field is the, and these windings are shorted. So we have the stator, in that the rotor, and this rotor is rotating. The stator is the, when the rotor is rotating, when the rotor is rotating, the field also changes linking with the stator. As a result, there will be voltage induced in the stator winding. Obviously, now the action will be generator action. What else? We have rotor continuing to rotate, field current maintained. Magnetic field is the, rotor rotates. As a result, the field, the flux lines linking with the stator will change. Change of flux d pi by dt will result in voltage being induced in the stator windings, and the stator windings are short circuited. As a result, a current starts flowing here. Actually, the very idea of short circuiting is to provide the closed loop. The current starts flowing, and this current flowing through the windings will result in I square R loss, and that I square R loss, the power is dissipated, it is lost, that energy is lost. Where from that energy is coming? That energy is coming from the energy stored in the rotor. And as this loss continues to happen, the energy stored in the rotor goes on decreasing. Because of the decrease in the energy of the rotor, the stored energy, that is the mechanical energy, half j omega square, the speed of the rotor will decrease. That is how we get the braking here. Okay, so it is, dynamic braking is typically converting this machine into generator operation, and we are having here the electromagnetic induction of dynamic type, dynamic electromagnetic induction, because the rotor is rotating na, rotor is rotating na. That's why the synchronous motor will now operate as generator, and that generation of electricity is from the stored mechanical energy. That generation of electricity gives rise to loss. That loss is taken, that power loss is drawn from the stored energy only. Hence, the energy stored becomes less, decreases, the speed becomes less. That is how we get the braking in the case of synchronous motor. So, we have the motor now acts as a generator, and the stored energy is dissipated in the windings, decreasing the speed. Braking happens. Now, if we want to control the rate of braking, if we want to make the braking to happen faster or slower, if we want to make the braking to happen faster or slower, that is here. If I want this braking to happen faster, what I need to do? Whatever energy is stored here, that I should take out faster. That means the energy dissipation here should happen faster. For that to happen faster, the effective resistance of this circuit we should be in a position to change. That is where we have the additional rheostats connected. These additional rheostats are controllable in nature. By controlling their values, the resistance values of these rheostats, we will be able to control the amount of energy dissipated and hence the rate at which the braking is happening. That is one part. The second part is, since there is a short here, just at the beginning of the braking, if we do not have any opposition except the windings, the current in the stator might be too high. We may have to control the magnitude of that. These rheostats will also help for that. They will also help, the rheostats will also help in controlling the current, the current in the stator windings during braking. So we can have two things here with the help of these external rheostats. One is the rate of braking, the second one is the magnitude of the stator current can be controlled. So the braking rate and magnitude of braking current, nothing but the current in the armature, can be controlled by connecting additional rheostats in series with stator windings. By varying these rheostats simultaneously, that's very important. These rheostats, there are three, corresponding to three phases. They are to be varied simultaneously. Something like you have seen in the machines lab, no, mostly you try to vary the rotor resistance of the induction motor, wherein you try to control the rotor resistance control. What you did there, you took three rheostats, and the three rheostats were put like this physically, and their jockey variable point were like this. Now I will have to move these simultaneously so that equal amount of resistance is added or taken out. Otherwise the operation will be unbalanced operation. How it was done in the lab? What you did, you remember, we had put a mechanical member connecting all the three sliding arms, sliding knobs. We had connected a crossbar. It was the crossbar like this. It was mechanically linking all the three sliding knobs, and we moved this bar. When we move this bar, all the three will move simultaneously. When we move this bar, all the three will move simultaneously, making the uniform change in the resistances. That part is to be kept in mind, sorry. And the next thing is, using a variable rheostat like this is the only approach? Not necessary. We can avoid the physical variation. We can make this variation of the resistance with the solid state approach. We discussed about this. Do you remember where? Yeah, I will give a pause, try to recollect. Varying the effective value of resistance in a solid state way without the physical variation. Where we saw this? Yeah, anybody? Yes, we discussed about this when we discussed about the induction motor, three phase induction motor drive control using rotor resistance control. Using rotor resistance control, wherein we use a solid state switch like a transistor, and using it and controlling its on time and off time, what we call that as duty cycle, the effective value of the resistances can be changed. So there is another possibility apart from this, that is solid state solid state control. That also we can have. That actually becomes makes the whole thing very compact. Solid state control. Okay, so now whether this or this will help us in changing the rate of braking and the control over the current in the stator windings. Of course, the method is having an issue, that is the energy is lost. There is loss. Energy is lost. Energy stored in the motor is lost. That is why the efficiency becomes less, the economy becomes poor, economy becomes poor, and there will be issues like temperature rise. A whole thing becomes little complicated, particularly when the motor rating becomes too big. If the motor rating is too big, maybe we will not be able to provide the corresponding rheostats at all. In such cases, we will have to go for, yeah, we will have to go for, what is that? Instead of wasting the energy here, you feed it back to the supply. You feed it back to the supply. That is where we have regenerative braking. Regenerative braking. Regenerative braking, we have the stator, we have the rotor, and from this stator we will have to feed back the energy to the grid. This is the grid. Okay, good. How that can be done? Are you able to appreciate this? This whole thing is the synchronous motor. Now I am keeping the field, rotor is running, electricity is produced here, it is operating as a generator. Now that electricity I will have to feed back to this. I have to have something here. I have to have something here, and that should act as power conditioner. What is that? Power conditioner. Why I call it as power conditioner? Whatever electric power I am getting here should be conditioned such that I can connect it to the grid, which is three phase. I will give a clue. It has to be three phase supply. It has to be of this phase sequence. It has to be of this frequency. All that is to be done by this power conditioner. So it has to be a solid state converter. Solid state, nothing but power electronic converter. Maybe using transistors, power transistors, or the SCRs. Is it okay? Okay, we will stop there. Next class we will continue.